Hello again. Today what we're going to do is we're going to start talking about some different types of chemical reactions. And so the first one that we want to discuss are what are called precipitation reactions. So a precipitation reaction generates what we call a precipitate. So what exactly is a precipitate? Well, what'll happen, and we'll show you an example in just a minute, but what happens with a precipitate is this is going to be a solid that is formed when you mix two clear solutions together. So I'm going to take two solutions of different ions and I'm going to put them together, and when I do, I'm going to form a solid from that. All right, and again, you'll see what it looks like in a moment. Now that solid, it's going to look cloudy and murky, but that solid can be separated from the remaining solution using three means. Either filtration, so you can run it through some paper that will catch the solid and then allow the liquid portion to come through. Through centrifugation, which is basically you take a test tube full of the material, you put it into a device that spins it very fast. That makes the solids go to the bottom and leaves the clear liquids on the top. And then finally, you can just let it sit. If you let that material sit, because the solid is more dense than the liquid typically, the solid particles will settle to the bottom of that solution. So we're going to take a look right now at what a precipitate looks like. So as we mentioned, a precipitate is simply what you get is a solid that you get when you mix two liquid solutions. So what I have for this example is I've got some sodium iodide that I've dissolved into the water that's in this graduated cylinder, and here I have a little bit of lead nitrate. So I'm going to add this lead nitrate to the sodium iodide, and we're looking to see if we're going to get a precipitate. Now, if it's a precipitate, you'll notice it'll get cloudy. Oftentimes you'll see a change in color. So here we go. I'm going to drop a little bit of this lead nitrate solution into the sodium iodide. And you can see that as each drop hits, you get the formation of kind of this mustard yellow precipitate. So I'll add a few more drops here. Now, how do I know it's a precipitate? I know it's a precipitate because, number one, I can't see through it. It's forming tiny particles of solid here, and those particles are opaque. You can't see through them. After a few minutes, if you were to watch for a while, you'll start to see some of the solids, they'll clump together and get big enough that they're able to start settling. So another thing with precipitates is that, number one, you're going to get a solid that comes from two solutions, and you can separate it. So I could actually separate this precipitate that's here if I use filtration or use a centrifuge, which is basically a device that spins it really quickly. Or you could simply just wait. We don't often have the patience to wait for it. That's why we go with filtration or centrifugation. But that is a precipitate, and we're going to talk a little bit more about that, why that precipitate formed back at the board. Let's talk about what we saw in the precipitate reaction that occurred in that graduated cylinder. Now, inside of the graduated cylinder, we had a particular solution. What I made is I basically made a solution of sodium iodide. So inside of there was some sodium iodide. Now the thing about sodium iodide is if I add that to a solution, these two, when it dissolves, these two break away from each other. And so what actually I had is not sodium iodide. Instead, it's sodium ions and iodide ions separated. Oops, that's not positive, that's negative. Let me erase the whole thing. Let's start over. You ready? Let's take a minute and talk about what we saw inside of that graduated cylinder. Now, before I added the drops to it, I had added some crystalline material, some crystals of sodium iodide into the water that was inside of that graduated cylinder. The thing you should know about sodium iodide is when you add it to water, it does not stay as NaI. Instead, it's going to break apart. These two pieces are going to break apart. We talked about that process where water surrounds them and pulls the ions apart from each other. And so what I actually am going to see in here is I'm going to see some sodium ions, the +1 charge, floating around, surrounded by water molecules. And I'm also going to see some iodide ions floating around in there. All right? Now, when I came in with the drops, so I had that dropper bottle, and we added some drops to it. And this was PB, lead nitrate. Now, specifically, this is lead 2 nitrate. It's got a +2 charge. But the way to think about this is, this was also in solution. So when those drops came out, the drops came out of here and went down to the bottom, or went down to the liquid here, I would basically be adding PB, NO3 taken twice to that, but that's not really the ions that you would see. Really what was floating around in here was lead with a +2 charge, so lead 2, and nitrate with a -1 charge. So the way to think about this is not as two full compounds, sodium iodide and lead nitrate. Instead, you should be thinking about this as this soup that contains all of these ions, the sodium, positive sodium, the positive lead, the negative iodine, the negative nitrate. All of these guys are really what's floating around inside of here. So what I want to do is see if I can come up with an equation for this. So let's start with the sodium. The sodium, will it combine with the lead? I'm trying to figure out what that precipitate was. Will sodium combine with lead? The answer to that is no. Why not? Why will the sodium not combine with the lead? Well, they're both positively charged. They would repel each other. So they would never combine. Would the sodium combine with the iodide? That's negative, that's positive, that's a definite possibility. But that sodium iodide was already inside of that graduated cylinder, and I didn't see a solid when it was just the sodium iodide. It was clear, it looked like water. That means sodium iodide cannot be the precipitate. What happens is, even if these two bump into each other and try to combine inside of that soup, they'll just immediately break apart. That's how soluble, that's how easily dissolved that sodium iodide is. It just would always exist as sodium ions and iodine ions, not ever as sodium iodide connected like a compound. So that leaves me only one possibility here, and that is the sodium could combine with the NO3. All right, so I'm going to go ahead and start writing a formula here. So I would say that I had NaI, and we know it was aqueous, it was dissolved into water, plus the lead nitrate was the other substance, lead 2 nitrate, and that's also aqueous. And when I think about what kind of a compound I'm going to get from this, all right, the sodium we know is going to combine with the nitrate. That must be what happened. If I want to kind of go over what we did here, I could break this up into Na plus, just like we did before, and I plus, I negative. That's a negative ion. All right, plus what I'm going to get from the lead is Pb 2 plus and 2 NO3 negative. Again, why 2? Because there's 2 of them right here. Okay. Now, as we discussed, we can start making combinations here. The sodium Could combine with this, with the iodine, but we know, again, it would just immediately break apart and give me this. The sodium won't combine with the lead. The sodium will combine with the nitrate. All right. I'll get to balancing this here in a minute. But that's one possible suspect to see who the precipitate is. Now, let's talk about the lead. For some reason, I'm just going to do the positives. We already know it won't combine with the sodium because they're both positive. It could combine with the iodine. That's a possibility. But if it combined with a nitrate, once again, we know that that was a clear solution. So it won't combine with these two because it would just immediately break apart again. All right, they would just break apart. So the other substance has to be Pb with a +2 charge combining with iodine that has a -1 charge. Now, is a 1-to-1 ratio going to work with this? Clearly it won't, because remember, my overall charge has to total 0. So I need a second iodine here to go with the single lead. That way I've got a -2 from the iodine and a +2 from the lead. Now, the question now becomes, okay, and actually, let me get this balanced before I go any further. Here I've got 2 nitrates, but only 1 here, so I'll need a 2 there. 1 and 1. Here I need a 2 here. And I'd have 2 of these. Yeah, I think that balances it. Okay, so who's the precipitate? I have 2 possibilities, all right? It could be this, or it could be that. So the way that we determine this is we have a set of solubility rules. I'm going to go ahead and put those solubility rules up on the screen, and we're going to talk a little bit about those, and then we'll come back and figure out which one of these 2 was the precipitate. All right, so what we see here is a copy of what we call the solubility rules. And these are just kind of some general rules, and there are some exceptions that tell you when a compound will dissolve or when it will stay together as a precipitate. So your first rule that you guys can see is nitrates. Basically, if you see a substance that has NO3 in it, it's going to be soluble. Nitrates are extremely soluble. So you won't have many precipitates that have nitrate. In fact, I can't think of any. The second rule is if you have a compound that contains alkali metals, so that first row in the periodic table, lithium, sodium, potassium, cesium, and rubidium, and also the ammonium ion, NH4. Those are usually soluble. All right, so most alkali metals, the first column, are soluble. If you have compounds containing chlorine, bromine, or iodine, they're generally soluble also. There are a few exceptions, though. So if you have chlorine, bromine, or iodine attached to silver, mercury, or lead, then those are exceptions, and those will typically form solids or precipitates. All right, so most of the time you see chlorine, bromine, iodine, it will dissolve, but your exceptions are silver, lead, and mercury. Most sulfates, SO4, are also soluble. All right, they're also soluble, and again, there are some exceptions there. There's lead, mercury, magnesium, and calcium sulfate are not soluble. Most hydroxides are just slightly soluble. Everyone says, well, what's slightly mean? Basically, you can say that most hydroxides are not soluble. All right, that's kind of what that means. There are a few exceptions. Again, the alkali metal sodium hydroxide or potassium hydroxide, those are both soluble. And barium, you see some of the other ones down there, calcium, barium, are going to be not soluble. That's what we mean when we say marginally. And then finally, sulfide, so it's just a sulfur attached to it, carbonate, chromate, phosphate, again, only slightly soluble. What that generally means is you can count them as non-soluble. All right, so with those rules, we're going to go ahead and go back to the question that we're looking at, and see if we can't apply those rules to decide what exactly is our precipitate. Coming back to our equation here of what happened inside the graduated cylinder, remember that we have two choices here that we need to decide on in as much as what made the precipitate. So which one of these two are the precipitate? Well, the one thing I know is rule 1 said nitrates, they're soluble. I think it was rule 2 that said that alkali metals are soluble. So I got 2 strikes against sodium nitrate being the actual precipitate. Both of those rules would say that this thing would just fall apart. So that kind of leaves us with just one left, and we would look at rule 3 to make our choice here. Basically, rule 3 says that chlorine, bromine, and iodine are usually soluble, but there's one big several exceptions, one of them being lead. All right, this was an exception to the solubility rule for iodine, which means our precipitate must be lead iodide here. So we would just add a solid right there to show what state that it would be in. So our precipitate, that yellowish, kind of mustard yellow solid that formed, that was lead iodide is what it was. Lead 2 iodide to be specific. All right, so let's do a little bit more practice using these solubility rules. And by the way, the solubility rules themselves, you can find them on page 150 in your textbook. And you should be expecting a quiz on those in the next few days. I'll give you details. Anyhow, so I'm going to ask myself a question here. We're going to use the solubility rules to hopefully work through this and see if we will get a precipitate. So would this reaction result in a precipitate? The steps you need to do here is first, if I look at these, I can see they're both ionic. How do I know they're ionic? These 2 are metals, that's a non-metal. And really, that's a polyatomic right there. Non-metals, metal. Anytime you're mixing your non-metals with your metals, probably going to be an ionic substance. So what would I get if I actually dump both of these into water? And I know they're in water because they're both aqueous. Well, if I put this in water, what I'm really going to get is I'm going to get some K pluses, okay? And I'm going to get a chromate ion. Okay, how do I know that this one's -2 on the chromate? Well, you can memorize these. That is a polyatomic. And so there's a list of polyatomics and their charges that are there. But I can also just use the compound that I find it in. I know that 1 chromate combined with 2 potassiums. And I know based upon its location in the periodic table, potassium always has a +1 charge. All right, just like sodium, it's in the same family. It's going to have a +1 charge. That means if there's 2 of them, to go with one of these, then this one must have a charge of -2, since its charge will be eliminated with 2 of those +1 charge potassiums. All right, moving on. Barium nitrate is going to be soluble in water. Why would it be soluble? There's rule 1, right? It's got a nitrate in it. This is going to dissolve. I know that nitrate, and this is just memorization, NO3 nitrate has a -1 charge. If there's 2 of them here, that must mean that barium has a +2 charge. Okay? You could also do that like we would usually decide what the charge of an ion is. Okay? You could find the number of valence electrons, decide whether it'll gain or lose. If it loses, which barium would do, it would lose 2, which gives it a +2. All right, so we need to think about what the possible products are here, and then we can apply our solubility rules to see if either one of them would be a precipitate. So potassium, it'll combine with this. I know it will. It's positive. That's negative. It would combine with the chromate, but we already know the chromate dissolves. When they told us this is aqueous, we know that these 2 will always break apart. that's not going to form a precipitate. All right. The potassium isn't gonna form a compound with barium because they're both positive. That means the only possible partner, I guess I should say, for the potassium would be the NO3. All right, since the NO3 is -1, the potassium is +1, it would be 1-to-1, but would that be a precipitate? Look at your solubility rules. Would this be a precipitate? It won't. Rule 1 says it's a nitrate. If you got a nitrate there, it's not going to form precipitate. So that one won't form a precipitate. The other one that I have, though, is the other positive ion that I have is barium. Again, I go through the same logic here. It could combine with nitrate, but that would immediately just fall apart. We know it does because this substance is aqueous. It won't combine with potassium because they're both positive. That means the only choice is barium, Ba chromate, CrO4. Now notice here, barium is +2, chromate is -2, so a 1-to-1 ratio works fine here. The question is this a precipitate? Well, if you look at your rules, I think it's rule 6, that has chromate in, or talks about chromate. Chromate is not normally soluble. And barium is also, it's an exception to some of the solubility rules, so it will tend to be insoluble also. So this guy right here is a precipitate. All right, you're going to get a precipitate out of this one. So I'm going to go through 3 more examples, but I'm going to clear the board first. So just a few more practice questions here. And again, we're asking the same question. Will we get a precipitate from these different reactions? All right. So remember, when something's aqueous, your steps are, first, break this down. Break it down into the 2 ions that you will actually get from this. So I know I'm going to get a potassium and I'm going to get a nitrate out of this one. All right, nitrate's -1, potassium's +1. You can hopefully see that knowing the charges on these polyatomics is really useful when you get to this kind of stuff. Here I'm going to do the same thing. I'm going to get barium. And I know that barium has a +2 charge. And I'm going to get 2 chlorines, each one with a -1 charge. So what are our possibilities here? Well, once again, this could recombine with nitrates, but we know that nitrates never form precipitates. So it won't do this. It would just break apart and give me the same 2 ions. Let me just draw those in. The potassium won't combine with barium because of charges. That means the only possibility is potassium chloride, KCl. Again, potassium's +1, chloride is -1. So a 1-to-1 ratio works fine. The question is, will that be a precipitate? There's actually 2 rules that say it won't. One is the rule on alkali metals, like sodium and potassium in this case. The other one is the rule on chloride. Chloride won't normally form precipitates unless you have those exceptions. I think it was mercury, silver, and lead were the exceptions. This is not going to form precipitate. Okay? Now the question is with the barium. Now the barium could combine with the nitrate. Okay, the barium could combine with the nitrate. But what do we know about nitrates? I mean, basically you're going to form BaNO3 with a 2 as a subscript because this is -1 and this is +2. Well, what we know about nitrates is they don't form precipitates. All right, this is just going to fall apart. And so what I would say in this case, because both possible products don't form a precipitate, we would basically just say that there is no reaction here. This soup of these ions would just float around, bump it into each other, maybe combining for a second, but immediately break it apart. So you get no reaction. There'd be no precipitate in that first example. okay? If I come over to this next one, instead of thinking of this as sodium sulfate, I should be thinking of this as sodium ions. There'd be two of them. And a sulfate ion that has a -2 charge. Lead ions, Pb, and that's got a +2 charge. And a couple of nitrates, NO3, with a -1 charge. Okay, I'm not going to take a lot of time going over the charges and stuff. If you guys have trouble with that, we'll talk. Again, I'm doing the same logic here. This could combine with the sulfate, but it would just fall apart. We know that it does because it's aqueous. This would never combine with the lead. The sodium would never combine with the lead because they're both positive. So that leaves me NaNO3 as one of my possible products. Okay? Question is, would this be a potential precipitate? Again, as soon as I see that nitrate in there, you guys, your rule 1, nitrate never forms precipitates. It's out. All right, now I'm going to do the same thing with the lead. I can see that the lead could combine with this nitrate, but again, we know that that's going to be soluble already. Basically, this came from lead nitrate. That means the only other combination could be PbSO4. Now, your sulfate rule, your rule in the sulfates, is that they're usually soluble, but lead is one exception. So this would be a precipitate that you would get in this second example, which is lead sulfate. You would get a precipitate from this second reaction. And breaking up the last one here, we've got K+, we've got OH-. Again, both of these are floating around in that solution. From the iron nitrate here, I would get Fe. Now, charge-wise, I know that nitrate's got a -1 overall charge here, and there's 3 of them. That means that to go with 3 of these -1s, there must be one that is +3. So this charge on the iron is +3. The nitrate, of course, is still -1. It always is. All right? Potassium. So again, we're going to go through this logic. Potassium could combine with OH. We know, though, that that's aqueous, which means it's going to fall apart. It won't combine with the iron. It may combine with the NO3 to give me potassium nitrate. Again, though, the nitrate rule says this is not going to be a precipitate. The potassium rule, the alkali metal rule, says the same thing. So that will not be a precipitate. The only other possibility then is, again, iron will not go with potassium, both positive. It could go with nitrate, but it would just immediately fall apart. That means the combination between those two is the only other possibility. Now, this iron was +3. Hydroxide is -1, right? So I got a -1 here and a +3 there. A 1-to-1 ratio will not work. All right? To balance out this +3 from the iron, I need 3 of these hydroxides. And what do we know about hydroxides? I think the rule was marginally soluble. So this would be a solid. We would say that would form a precipitate, which we would call iron 3 hydroxide. All right? So this is how you do these, you guys. You're going to break them up into ions. You're going to kind of mix the ions and see what possible products you're going to get. Keeping in mind that these are already soluble, so recombining the sulfate and the sodium gets you nowhere. You just kind of keep going in a loop here. All right? And then figure out what your possible products are and apply the rules to them. That's all there is to it. All right, so this is solubility and precipitation reactions. What you guys are going to do is we're going to give you a little bit of practice, and we're going to work on some of these on our own.